Now we want to spend some time talking about similar problem, but pH of weak base solutions. So we saw that when we're dealing with weak acids, it's always the same idea. The reaction of a weak acid with water produces hydroniums. You have the same type of equilibrium constant expression, and you're solving for X. You always can use the approximations. So that when you're solving the pH of a weak acid, it's always the same kind of process. For a weak base, it's still very standardized and follows the similar idea. Just now, the reaction produces hydroxides instead of producing hydroniums. One of the things is that when you solve for X, you're getting the concentration of hydroxide. So you can take the negative log of that to get POH, which you can relate to the pH via our equations. It's a little bit different, so it's kind of a different processing step on the end, but still the same idea. ICE table works the same way. Kb, also, usually those values aren't tabulated. So you need to look up the Ka of the conjugate acid and use the relationship of those based on the fact that the product is going to be equal to Kw, so you can figure out what Kb is. Kb is still, because it's a weak base, Kb is still less than 1. It's usually a small value. You can still make the same approximations, usually, that you can make when you're dealing with weak acid solutions when you're trying to figure out the pH. So overall, it's the same general idea, just a couple different, just kind of a couple additional steps, namely calculating Kb, and then you're actually getting the POH and you have to relate that. But otherwise, it's the same overall process of working with the ICE table, solving it. The algebra is all going to be very much the same as with the acid. The X that you get is a different thing. So the algebra is the same, but kind of the chemistry wrapper is just a little bit different. So let's do an example. What is the pH of a 0.010 molar solution of cyanide?
All right, so again, we can see we want what is the pH of a 0.001 molar solution of cyanide. And so I want the pH here. And that's always going to be a description of what this solution looks like once I reach equilibrium, once the reaction happens. And so what we want to think about is, well, what is Cn minus, what is cyanide going to do in water? So is it an acid? Is it a base kind of thing? So this can't be an acid because there's no hydrogen in there. So then the question would be, well, is it a base? And because it is an anion, chances are it's going to be a base. And we can see that the conjugate acid, so my conjugate acid would be HCN. We know it'd be gamma plus, and we can see that HCN is a weak acid. So HCN is hydrocyanic acid. That is a weak acid. So because this is a weak acid, because the conjugate acid is weak, then that means Cn minus is a weak base. So what that means is that when you dissolve cyanide in water, you produce hydroxides. You produce some hydroxide that will then, change and affect the pH of the solution. It would be a basic, turn it into a basic solution. And so the kind of standard reaction would still be the Cn minus ion reacting with water. We know it's weak, so it'll be in equilibrium, and it will act as a base. So you make the conjugate acid plus hydroxide. And so what we're still looking at, if we want to know the pH, we want to know this amount of hydroxide that is present, right? What is the amount of hydroxide? What's the concentration of hydroxide at equilibrium? And that's going to be determined by basically, or we can figure that out, calculate out that value, again, by using an ICE table. And so what we'd want to do is we'd want to look at, in this case, we have our IC. And this is going to work very similar to my weak acid problem. Water doesn't show up because it's a liquid, so it's not an equilibrium constant. I have an initial concentration of the base in this case. I have no of my conjugate acid or hydroxide, so those are going to stay at 0. That means my shift has to be to the product side. Acid-base chemistry, all of my coefficients are 1, so I just get the X right there. 0.01 minus X, X, and X.
So that the ice table, you know, outside of what the reaction is, it looks very identical to the weak acid ice table. It's always the same idea. Initial concentration of acid or base. You always shift to the products. It's just going to be X's over there. My equilibrium constant has a different name. It's called KB now because this is functioning as a base. So hydroxide is one of my products. Cn minus. And I can go ahead and plug those values in. I get X and X, 0.01 minus X. So this tells me that KB is equal to X squared, 0.01 minus X. And so we can see solving it is going to look very similar. Just like we did with weak acid, a weak base, we expect that the equilibrium constant is going to be low, so we can probably make an approximation. One of the things we will note, though, is we're not given KB, so we assume KB is low. So one of the differences when it comes to working with a weak base is, you know, where does KB come from? What's that equal to? So we know for the approximation, we're probably going to be able to do 0.01 X is just going to be equal to 0.01. And so that would help our algebra. But so that would help us deal with this side. We also need to deal with the other side of the equation. We need to plug in a value for KB. At some point in time, I'm going to need to do that. And so we know that the tabulated data is always KAs, the acid dissociation constants. To get the base, we can use the fact that for a conjugate pair, so Ka of HCN times Kb of my Cn minus is equal to Kw. So Kb of Cn minus is equal to Kw divided by Ka. So 1 times 10 to the negative 14th over HCN, the Ka I can look up, 6.17 times 10 to the negative 10. So we can always look up Kas. And I get that the Kb of Cn minus is equal to 1.6 times 10 to the negative 5th. So that works. We got the Kb. And when you're dealing, so this is like one of the first differences that comes up when you're working with weak bases, that you generally have to calculate the Kb on your own. Sometimes you'll be given it, but a lot of times you got to calculate it on your own. So that would deal with our left-hand side of the equation. So overall, we're going to get Kb is equal to X squared divided by 0.01, and that's what we want to solve. So Kb is equal to X squared divided by 0.01. We can multiply that out, isolate the X, take the square root. So again, the algebra actually solving the problem is very similar to the weak acid problem that we had. We can plug in the value for Kb that we calculated, 0.01 times 1.6 times 10 to the negative 5th. And I get that X is equal to 4.0 times 10 to the negative 4. Whenever we make an approximation after we get our X, we need to check that the approximation was valid. So it's going to be change divided by initial times 100. So the change is the X value. So 4.0 times 10 to the negative 4th divided by the initial is 0.01 times 100. That's 4%. So in this case, we are close to this not working, but less than 5 means the approximation is valid. We're pretty loose with our threshold because we really do want to avoid doing a quadratic formula. It really does actually end up introducing a great likelihood of making mistakes. And so we want to be sure that we avoid that and we just use our approximation. So now I've got my x. This x from the ice table is equal to the concentration of hydroxide. So my concentration of hydroxide is equal to x is equal to 4.0 times 10 to the negative fourth molarity. The pOH is equal to the negative log of the concentration of hydroxide. So what we want is the pH, which comes from hydroniums. Bases don't make hydroxides, they make hydroxides. So we cannot directly calculate the concentration, the pH from this number. So we have two strategies. We can either calculate the pOH first. So in this case, pOH is the negative log of 4.0 times 10 to the negative 4. And we would get that the pOH is equal to 3.40. And then from that, we can use the fact that pH plus pOH is equal to 14. This is just a general relationship when you're dealing with the pH and pOH of a solution. I have 3.4, so pH is 14 minus pOH. That's 14 minus 3.40. pH is equal to 10.60. So when you're dealing with weak bases, really the weak base creates hydroxides. So you're going to get the concentration of hydroxide at equilibrium. You can use that to calculate the pOH and relate that to the pH. Alternatively, you can take the concentration of hydroxides and turn that into a concentration of hydroniums. You can use the equation that Kw is equal to the concentration of hydronium times the concentration of hydroxides, and then take the pH of that. So no matter what, you should get the same pH value. It's just a matter of whether or not you use you turn it into the power first and then go to the hydrogens, the hydroniums, or you go to hydroniums and then do the power and the pH. Either way works, and you should get the same number. But overall, weak-based pH calculations work very, very similar to weak acid pH constant calculus. It's an ice table that looks very similar. You use an approximation in the same way. The actual algebra you do calculate out of the approximation is identical. All of this works kind of in the exact same way. The only difference is that generally you have to calculate the Kb yourself based off the Ka of the conjugate, and then you just have to be mindful that that you get, if you take the negative log of it, you're actually calculating pOH, which is not quite what you want in your answer. What you want is pH.
Participation 10-10. Question 3. Ammonia, NH3, is a weak base with Kb equal to 1.8 times 10 to the negative fifth. What is the pH of a 0.15 molar NH3 aqueous solution? This is the third question on participation 10-10 due Friday, October 10th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, ammonia, NH3, is a weak base with Kb equals 1.8 times 10 to the negative fifth. What is the pH of a 0.15 molar NH3 solution? Three questions on participation 10-10. You want to find all those questions, get them answered, get those answers submitted over on Blackboard. Answers to that will go live on Friday. Otherwise, this is the final video for the week. Week 7 homework due Saturday, post-lab due Sunday over on Blackboard about determining KC. If you have any questions about anything, let me know. Otherwise, enjoy your weekend. I'll see you next week. We do chapter 14 again. Next week is all chapter 14. It's a long one. I will see you there. Bye-bye.